Hi there, welcome to a presentation on parametric functions and their differentiation. By the end of this presentation, you must be able to explain or understand what is a parametric function is and what is the process of its differentiation, especially to find the first derivative and the second derivative. Let's start this way. Here is our great continent of Africa, and as we all know, we are in South Africa. Maybe some of you might be wondering now, what has this to do with parametric functions? Let's look at a map like this one, which is actually a road map of our country. Like, for example, let's look at one of the major national roads, like what we know as National Road number 1, the road which starts from Cape Town to the border in north in Beitbridge. So here's the road, is seen here as a kind of a curve in blue. So how does this link with the parametric functions? Let's say on this map, let's impose a system of coordinates. In this case, you've got the x-axis and the y-axis. And we all know that in our system of coordinates, normally we plot curves or functions. In this case, believe me, this curve, which is represented by this rod here, we can find a mathematical way of describing it via any equation, and then we have a kind of a function which can call y equals to f of x. But if you imagine a truck driver traveling from, let's say, the Cape to anywhere in the country or further north at a particular time, at a particular time, in this case I'm talking about time, let's say t, this truck driver is at a certain position somewhere there, x, y. Now, in that position, the truck driver will be at that position at a particular time. In this case, this tells us that x, actually the coordinate x, is a kind of function of time, and the coordinate y is a function of time. This takes us to what we call parametric equations. This curve which we have here, we can describe it by some equation x, which is an expression of time, and there's some equation y, which is an expression of time, and those equations are going to be called parametric equations. This is what I'm talking about. Let's say we've got a function there, then we've got a function of time y and a function of time x. In other words, we have if we want to plot this function on a system of coordinates like we've seen, we would plot a curve like we've seen like that. But now if the function is given in terms of its parametric equation, we'll still plot the curve, because at each time we'll have a coordinate x and we'll be able to calculate the coordinate y. So then we can position the track somewhere there at x, y coordinates. So these two equations, which are given in terms of time here, are going to be called parametric equations. And you know, our topic is parametric functions and their derivatives. So in this case, if we're given a function like this and given in terms of parametric equations, we're going to call it a parametric function. Now, our big question at the moment is, now, if we're given a function, we don't even know the expression of x of that function, but it's just given in terms of a parametric equation. How can you compute the first derivative dy dx? Now, to understand that, please lock your system with my explanation and try to follow this following. So, for example, for a start, let's say we've got a parametric equation 2t squared and a parametric equation for x, which is t minus. So we can see that if we take t equals to 0, like in this case t is representing time, and the t actually is what we're going to call our parameter. If we take t equal to 0 and we compute these coordinates here, we will see that we'll be at a point for 0 here, we substitute 0 there, we get minus 2, which will be the coordinate x, and the 0 here will give us 0. So in other words, we can plot this point. So if we we run t through some interval of time, we can get points for this, coordinates of points for this curve. Then we can end up plotting it on a system of coordinates. So now notice that having t here, having x of t here, and knowing that y is actually a function of x, and the derivative we're looking for the derivative dy dx. So how can we calculate that? Let's try to understand the following. In this expression, we can get exactly that x is equal to t minus 2. And then that means exactly that t is equal to x plus 2. So in other words, here I've managed to express t as a function of x. So now if I go back to the equation which had where we had y defined as y function of t, I can now substitute this t by t as a function of x, and I get an expression like this. Now if I now ask again, how can we now compute the derivative, the first derivative dy dx? Then this is what we can do. Now we have that function now defined as y, defined as a function of t function of x, and then we want to compute dy dx. So all what we can take advantage of here is the chain rule. So what can we do now here? We can just say dy dx. Remember, when we differentiate the function, we differentiate in this case the immediate function dy dx. Remember, when we're differentiating a function y, we differentiate with respect to its variable. So in this case here, we say dy dt, then we get dy dt, and we must recall that whenever we differentiate a function, we must also differentiate the argument. But now the argument of y here is t, and the t is dependent on x. Then we would multiply here by the derivative of t, multiply the derivative of t with respect to x. So I repeat this. What have I done here? We're differentiating y, a function, with respect to x. So we've managed to see that you can express t as a function of x this way. So now what you can take advantage of here is the chain rule. So now say the derivative of y with respect to x is the derivative of y with respect to its argument, which is t, then we write dy dt. And we know that whenever we differentiate a function, we must multiply by the derivative argument. The derivative argument of y is t, but t depends on x. Then we multiply by the derivative of t with respect to x. Now, to make sense or make this more easy to use, we now think of the following. Remember, if you've got a fraction a over b multiplied by c over d, we can easily translate this to division as a over b divided by d over c. Because remember, when we are dividing like this, what we do, we would invert the divisor, which is here, and then multiply the number, the fraction which is being divided. So trying to take advantage of this kind of manipulation, we can change this to dy dt divided by dx dt, which makes sense because our parametric equations is y, a function of t, and the x defined as a function of t. So now the manipulation we have done here, it tells us that if we're given a function in terms of this parametric equation, to find this derivative with respect to x, then what we have to do is we simply have got to find the derivative of y with respect to t and divide that by the derivative of x with respect to t. Now that takes us to this kind of a summary. Here are the parametric equations, and these parametric equations, we understand that they define a function which we can plot on a system of xy coordinate, a function which you can call f y is equal to f of x, and you can plot it on the system of coordinates like that, where we've got x here and y, and recalling that the derivative, the first derivative is actually the rate of change of x, of y with respect to x. So now this derivative here will be actually giving us the rate of change of y with respect to x on this type of a graph. So this is summarized here by this formula. This is what we get. Now, going back to the equations which we have seen before, we have got an example here which says, let's say we're given y is equal to f of x by means of his parametric equations. Sorry for a spelling mistake there. And we are required to find y prime. Remember, y prime is another notation for dy dx. So according to what we have seen, dy dx will always be dy dt divided by dx dt. So what we can do now, we can come to these equations simple and say dy dt, which you can also denote by y dot. And here we're trying to make a difference between this y prime and that, and then this will give us 4t, applying our power rule there. And on the other hand, we have to get dx dt. Another short notation for that, you can just say dx dot, and then here what we get is 1. Therefore, now our first derivative with respect to x dy dx will be the quotient of these two derivatives. In this case, this is going to give us 4t divided by 1, which simplifies to 4t. Now, this shouldn't confuse you. This is not suggesting that this derivative is always going to be equal to that. This is just a simple coincidence. You will see later on with different examples. Now, let's now proceed with the following. Let's say now we want to calculate the second derivative of this parametric function. In other words, we're now searching for the second derivative dy 2 dx power 2. For that, we will have the following. For the first derivative, the function will go to y in terms of x, the equation, parametric equation, and here we've got x in terms of x. And we've seen in our previous example here, this derivative actually comes as an expression of t. So now here, this is equal to an expression of the parameter t. Now when we search for the second derivative, now our parametric equations are actually the first derivative dy dx in terms of t, and we've got x again in terms of t. In other words, in this part here, y is going to be replaced, this y, instead of being y, is going to be replaced by dy dx. So now, this equation is going to, the second derivative now is going to look like this. We will say d2y dx2 is going to be equal to, for this, if we replace this y by dy dx, then this is going to look at the derivative equal to t of dy dx, because that's the dy dx now here plays the role of y. So you can see the y there, here dy dx. So then divided by, then we take the derivative to x, then this will be dx dt. So now this expression will actually give us the second derivative with respect to x. And remember our when we're dealing with distance time functions, the first derivative, or if y was a distance function, the first derivative represented what we call what we know as velocity, and the second derivative, in this case the second derivative for time, represented what is acceleration. So in other words, this dy dx will give us the first derivative, and this one is going to give us the second derivative. So we're going to again talk in terms of velocity and accelerations in this chapter. So now, summarizing what we've discussed, this is exactly what we've got here. We never want to get the second derivative, given the first derivative as our first parametric equation, and the x as the second parametric equation. Then what we have here, we use this to calculate the second derivative of y. So looking at the example again, now let's look at the same example you've given now here. This now we're looking for the second derivative. But remember, we can never get to the second derivative without going via the first derivative. So what we can start doing for given a problem like this, we can start by getting dy dx, which we know now is dy dt divided by dx dt. We saw this derivative of this close to t was 4t, and here the derivative was 1. So we've got now here, we've got 4t. Now for the second derivative, which is now d2y dx second, then we follow the formula we've just seen here. We need to differentiate dy dx with respect to t. So what we're going to do now, we're going to say du dt of dy dx, which is this. Then we put here 4t over dx dt. Now differentiating here, we'll get this. We're going to get this as a 4, and the dx dt, we have it as 1, and then this is going to simplify to 4. So then, if we're dealing with distance time functions, this will be the velocity, expression for velocity, and this will be acceleration. Now this takes us to this type of discussion. In this case now we can talk in terms of velocity and acceleration components. Let's say now we've got that sketch of the curve as our route, our N1 route, which we've got on our rational map, and then we get that between these 2 points, we know that if we get the average slope for that, we can get what we can call the average velocity speed for the track which is moving along that road. So now what we have here is if we get our parametric equation is y of t and the x of t. Now if we differentiate y of with respect to t, we get what we can call vy in this case, which is our vertical component of the velocity. In this case, vy will be represented there. And when we get dx dt, we'll get that as bx, and we'll call that our horizontal velocity component. So now, in this case now, if we were to get the magnitude of this velocity, I think it's clear that here we've got a right angle, then the magnitude of the velocity. Remember, velocity here will be given by dy dx. So the magnitude of velocity, which we denote here by the absolute value, is going to be given as the square root of, using Pythagoras theorem, as the square root of vx squared plus vy squared. So similarly, we can talk of acceleration component, which I'm going to leave for you for individual study. Otherwise, at this moment, I hope you are aware of what is a parametric function and what are parametric equations. And you can also be able to determine your first derivative of a function y with respect to x using parametric equation. And you can also be able to determine your second derivative with respect to x using your parametric equations. Otherwise, for now, I would like to say thank you for listening. Please get to your textbook and your additional notes and do practice of this type of exercises.